In this video, we're going to analyze a few infinite series. The word series you should think of as being synonymous with sum, and a finite series would mean we're summing up a finite number of terms, but an infinite series is one in which we're determining the behavior of an infinite sum, which seems impossible, but we kind of work around it. But in any case, you can see that the examples below are examples of infinite series. The dot dot dots at the end of examples 1 and 2, and the infinity at the top of the summation sign in number 3 indicate that these are infinite series. So we're interested in finding whether they converge or diverge. So again, to converge would mean that the limit of partial sums exists. All right. So what do I mean by that? Well, look at example 1. The first partial sum would mean just to add up the first number, which is a 1. The second partial sum would mean to add up the first two terms. That's 1 minus 1, which is 0. The third partial sum would be the first three terms, which would be 1 minus 1 plus 1, which is 1 again. And the fourth is 1 minus 1 plus 1 minus 1, which is 0. So you can see that this generates a list of values, right? So S1 is 1, S2 is 0. This is a sequence that has no limit because it does not approach one value. So therefore this series diverges. Let's look at the second example. We've got a 9th plus a 27th plus 1 over 81. So it looks like the terms are getting smaller, but it also looks like we're multiplying by the same constant every single time. So to get from a 9th to a 27th, we're timesing by a third, and from a 27th to an 81st, we're timesing by a third again. So so you could think of this as you could factor out a 1/9. If you factor out a 1/9, it's a 9th times 1 plus a third plus a 9th, etc. So this is a type of infinite series that we actually know a lot about. This is a geometric series. It's an infinite geometric series in which our R value is equal to this is geometric, and our R value is equal to a third, which is less than 1. So this must converge. So what does it converge to? Well, fortunately we have a nice formula for that, which was covered hopefully earlier in your math experience, but this would be a 9th times our first term, which is 1, over 1 minus the R value, which is a third. So this is a 9th. This is a 9th times 1 over 2/3, which is 3/2, which is a 6th. Alright, and then example 3, we're using summation notation. So let's write out the first few terms. Actually, before I do that, I think I might actually change how this looks in the inside, because that'll reveal the behavior of the series. N over n I can think of as 1, and 1 over n would be added. So I'm going to view it like this. So if you write out the first term, you get 1 plus 1, which is 2. Plug in a 2, you get 1 plus a half, so you get 1 1/2. I'm just going to write it like this, I think. Plug in the third term, you get 1 plus a third, and it's just going to keep going on like this. So hopefully you can anticipate that the partial sums the partial sums are going to keep growing without bound. If you think about it, this has to be, I mean, this is, whatever this series is, it's definitely bigger than this series. Like, so let's assume it has a sum. It's got to be bigger than the series where we're just adding 1 every time, right? Because every term has a 1 in it, and we're adding a positive number. But this clearly diverges, right? Because the first partial sum is a 1, the second partial sum is 1 plus 1, which is 2. The nth partial sum would be n. And clearly that goes to infinity. So we can see that this diverges. And I mean, your intuition I think was enough to answer that, but I kind of snuck in a little comparison, which is something we'll revisit later on. But I mean, if you compare this series to this one, term by term, the one on the right is bigger than the one on the left, but the one on the left clearly diverges, so the one on the right must as well. Let's look at a couple more examples. Example 4 looks like an alternating series, and ignoring the signs, you can see that each term reduces an absolute value by a half, which suggests that this is also a geometric, where my r value your r value is negative 1/2. But since the absolute value of negative 1/2 is less than 1, we know it converges. So this equals our first term, which is a 4, divided by 1 minus the common ratio, which is 4 over 1.5, which is 3/2, which is 4 times 2/3, which is 8/3. All right, and lastly, we've got n squared, and this can be answered pretty quickly because that's just 1 squared plus 2 squared plus 3 squared, and the limit of partial sums is clearly going to go to infinity, so there's not much to talk about there.